Welcome Physics 30. Sorry I couldn't be there today. Hope this video lesson works really well for you. You can pause the video whenever you need to just to kind of catch up. I'm just going to ramble on through like I usually do. So let's just recap what we did yesterday in class, or something more close to what we did yesterday in class. So yesterday we were talking about like these two forces that are possibly holding together our nucleus, right, of our atom, where we have protons really close to each other, femtometers apart, and they're causing this huge force repelling each other. And then we got this tiny little gravitational force trying to hold it together, and we're thinking, that doesn't quite work. You can see here that the Fe is times 10 to the 36 times larger than the gravitational force. The electrical force is just going to rip everything apart, right? So we discussed that there must be another force holding together. So one of our four fundamental forces, right? This other finger we haven't talked too much about. We have gravitation. We have our electromagnetic. We kind of tied them together. They got unified by what we call the grand unification theory. So they get unified together as the electromagnetic force. And then we have our strong nuclear force. And this one over here is our weak nuclear force. So our strong nuclear force is going to be holding things together. And the strong nuclear force only applies for like within a few femtometers, within the size of the atom or the nucleus itself, right? Not even the atom. The atom's 100,000 times larger than this nucleus. So this strong nuclear force only exists within that tiny little fraction of the atom inside that nucleus there, right? So to remove one of these nucleus, you're going to have to require a little bit of energy to do that. You have to overcome this force. And that energy required to overcome that force, the work to be done, because remember, force times distance is energy, it's work. To overcome that strong nuclear force, we had to add some energy to it, right? So this energy is called the binding energy. Right? This energy is required to separate all of its pieces. And what we've noticed, and what scientists have noticed, is that when you take all of those pieces, say this first one over here, I'm just going to highlight it. When you take all the pieces of this is the carbon, this example of carbon-12, it could be anything. You take all the pieces of carbon-12 and you separate it into its pieces, the pieces are more massive, right? So you can think of it either one of two ways. Like when you separate them, you got to add energy to the pieces, and the energy's got to go somewhere. And I talked about this in the last chapter, last unit, is that energy and mass are essentially just the same thing. So when I add energy to something, it doesn't go anywhere else. It's going to just go into the mass. And the objects are going to get more massive when you pull them apart. Or vice versa, when you put them back together, they're going to lose that mass and become energy to hold it together, this binding energy that holds everything together. But the mass of them together is smaller than the mass of them apart, right? So there's this, what we call a mass defect, where the mass on one side, the nucleons, just the pieces of them apart, is bigger than the mass of them all being put together. And we can find the mass defect pretty easily. We can just find the two masses and just subtract the two sides. Final minus initial, whatever. Usually we just put it as a positive number anyway, but you can think of, I've lost mass, I've gained energy, or I've gained mass, I've lost energy, because there's a mass energy equivalence there. If one goes up, the other one has to go down to match it. And we can use this formula, E is equal to mc squared, to help us find out what that binding energy is, or find out what that mass defect is, depending on what we're given in the question. Okay, so let's actually do one. I think I've already started this question up. We didn't get very far. I think we found, at least in one of the blocks, we found this mass defect here. If you want to skip ahead a little bit to get to that point, then that's okay. All right. So what we're going to do here, I'm just going to recap. So it says here, let's just determine the pieces in kilograms. They want to do it in kilograms. You could do it in atomic mass units, and we'll do the conversion. It's either one. I'm going to actually, it says in kilograms. I'm not going to do that. I'm going to do the atomic mass unit way. I know it says expressed in kilograms. But But then down here, when I have to find the binding energy, we're going to talk about that, is that when we use the E is equal to mc squared formula, our masses have to be in kilograms for sure. It's kind of like when we had the electron volts, very specific formulas, we had to use the electron volt version of some numbers, and some we had to use the joule version of some numbers. Or sorry, yeah, the joule one. And most of the time we had to use the joule one. In this case, yeah, we've got to use the kilogram one because that's the majority of masses on our formula sheet here. So let's go back up here. So we want to determine the mass of the pieces of each of the nucleons that have been separated in carbon-12. And we discussed this already. There's 6 protons, there's 6 neutrons. So I can quickly add them together and say that, let me just get a marker here. We could say that the mass of my nucleons, so this is for the nucleons here, is 6 protons, because we're talking about carbon-12, plus 6 neutrons. Okay, so we're just going to add all these pieces together. So we look at this little chart down here. It tells us some of the masses of protons and neutrons. I'm going to stick with the atomic mass unit version right now. I know the question specifies otherwise, but it just makes it a little bit easier to do the math this way. I don't have to deal with all these times 10 to the negative numbers. All right, so we have these two masses, atomic mass units, just another way to represent kilograms, kind of like electron volts and joules. But now we have atomic mass units and kilograms. All right, and we quickly do the calculation here, and we get 12 point something. So the individual pieces weigh more, I'm just doing the calculation here on my calculator, weigh more than the pieces put together, because this atomic mass units were defined by carbon-12 to be 12, right? And this is more than 12. So we got 12.0956646 atomic mass units. Now, I'm adding a lot of decimals here because we're going to need those decimals for the precision of the question. I'm not going to round too soon here. So I'm just going to leave it there. We're going to have to change this eventually to kilograms, but I'll do that in a later step. Yeah. So we also know that the carbon-12, the nucleus, with the same pieces, with the same pieces, it has this 12 pieces, it has 6 protons and 6 neutrons. The nucleus itself is 12.000 atomic mass units, exactly 12. That's how they defined atomic mass unit. So there's a difference between these two numbers. The pieces that make it weigh more than the pieces together. The same pieces. So we have what we call a mass defect. So we can find that mass defect by just going like final minus initial. I don't know what the final is here. Let's just say the final in our situation is the 12 number. And we're going to minus the 12.09, on this calculator right here, 5646 atomic mass units. So I minus the two numbers, so we're going to get this negative number. We're going to minus 12. All right. And we get a negative 0.095646 atomic mass units. Now, the reason I left the negative in there is because I've lost mass as they come together. If I lose mass, because the mass energy equivalence here, so mass energy equivalence, how do you spell equivalence? Equivalence? Yeah, okay, close enough. That if I have a change in mass, that means my energy must change the other way though. Right? So my mass goes down, my energy's got to go up. They're not exactly one-to-one, right? You have to do a calculation because of the E is equal to mc squared formula, but that's essentially what it is. One goes down, the other's got to go up. So if I lose mass, I gain energy. And how much energy is that? So we can calculate that in the next line here. It says here, find that binding energy. So to find the binding energy, I can use this formula. E is equal to mc squared. I'm going to put the deltas. You notice on the formula sheet up there somewhere that there are these little deltas. It's just saying if I lost mass, I gain energy. But if you ignore the deltas, that's okay too. Right? You could just also just ignore the fact that the m is negative at this point. Right? Oh, I'm going to sneeze. Sorry. Okay, but before I go too far with this formula, I need to change that atomic mass unit into kilograms. So we look at our formula sheet. 1 atomic mass unit is the same as 1.66 times 10 to the negative 27 kilograms. I'm just going to set up a little ratio here. So if I have negative 0.095646 atomic mass units, how many kilograms does that represent? So we just do a little cross multiply divide here, and we can find out that the mass defect in kilograms, okay, so let's just quickly do this, times 1.66 times 10 to the negative 27. Now that 1.66 times 10 to the negative 27, that's just from our formula sheet. It's the last constant on the constant chart. You want to use 3 sig digs there. If you look back a couple of pages, there's a bunch more sig digs there. I think in the video from yesterday, there was even more after that. All right, but for the 3 sig digs, if they don't give you that number in the question, just use the number on the formula sheet. So I'm going to multiply them, cross multiply divide here, and we get 1.5877263 times 10 to the negative 28 kilograms. So a really small number. So this is kind of why they're trying to avoid scientific notation by having this new unit. All right. Okay. So now we know the mass, change of mass. Technically, it's a negative number, right? So it is going down, right? But when we come to the calculation, if I have lost mass, I gained energy. So we're just going to drop the negative. Technically, there could be a negative in the formula, but I'm just going to drop the negative here. 1.58 times 10 to the negative 28 kilograms. I'm going to times it by the speed of light squared, and that's going to give me my delta E. Right? And then we just have to figure out what the units are going to be. So we got 1.43 times 10 to the negative 11. And because this is energy and we use kilograms, meter per second, all that stuff, we get joules. Okay, so this is a really small amount of energy. And usually when we talk about small amount of energies, we like to talk about them in electron volts. So maybe we can change this to electron volts. It doesn't specify. I'll just leave it that way. But the formula is going to spit out joules. If I give you electron volts as an energy, you're going to change it to use this formula properly. But there we go. So that's the binding energy. This is the energy binding everything together. Now, this is the binding all the nucleons together. So this energy is being shared between all the nucleons. So you can say somewhere like in here, so use a little different color here, that this energy is for all 12 of the nucleons. It's being shared between all of them, okay? But the better way to represent this kind of energy, this binding energy, is not for all 12, but if I'm going to try to compare it to some other element, because other elements have different number of nucleons. Like uranium-238 has 238 nucleons, right? It's going to have a huge amount of binding energy, but sharing it between a larger amount. So if I want to compare elements together, I may want to figure out how much is it per one of those nucleons, kind of scale it down. And you literally just do the math. If this is the energy for 12 nucleons, right? Maybe I can write that a little bit differently here. I can't erase this for some reason. Okay, it doesn't want to go away. Why did I erase that? Joules. Okay. If this is the energy for 12 nucleons, how much would it be for one nucleon, right? Because the slash, the per 12 nucleons makes sense too. So we literally just do the math. If I want to figure out per nucleon, so I'm going to write this down here. So per nucleon, we just take the number and divide by how many nucleons there are. So we divide it by the 12 nucleons. And this is going to find out how much energy is being shared, or taking the shared energy and find how much energy one nucleon is using to hold on. So I divide by 12. So I get 1.19 times 10 to the negative 12 joules per nucleon. Okay. Now, I didn't ask for that, but the reason I pulled this up is because this is going to be a very useful way to compare different atoms and how stable other atoms are, right? So if I were to go to the next page, if I were to do this calculation over again for all the different atoms and then find the per nucleon energy, I can create this chart on the next page here. So this is our nice little chart talking about the energy per nucleon. Okay? You can see it starts off pretty low. Down here, there's only 2 nucleons. It's being shared between the two, but there's really not much of a mass defect here. And then as you add more and more nucleons to it, the mass defect is starting to go upwards. That means the energy is going to go down or whatever. Is going to be the same. They're both going to go up, essentially. But I also have more nucleons. So the number's not going to jump up. We're talking about mega electron volts here. These are pretty big electron volts, right? Like if I were to convert this to electron volts, it'd be pretty large, right? Divide by 10 to the negative 19, that's going to be pretty big. I don't know where this is carbon, so where's carbon on my list here? It'd be somewhere in this here, right? You can see it. So as it goes up, this energy, the energy is always going up. So no matter where you are in this chart, the energy is just going to go up, 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 because the mass defect is getting bigger, 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 because there's more and more pieces. But because we have more pieces, when I take that bigger and bigger and bigger number and divide by how many nucleons there are, eventually we hit a peak, and then it starts going back down. So tin, uranium, they have lots and lots and lots of mass defect. They have lots of binding energy. But when you divide by 50, and you divide, or so not 50, 120, and you divide by 238, the number gets smaller. Okay? So this informs us that the more energy there is per nucleon, the more stable it is, right? So the greater the binding energy, just look up here, the greater that binding energy per nucleon, the more stable the nucleus is. You can see right here, then iron, 56, is the most stable there is, right? Right beside that, you'll probably see lead. So like when you talk about things decaying, they usually decay to lead because it's also pretty stable, right? So what's also very interesting about this when we talk about fission and fusion, fusion is taking like 2 smaller things and fusing them together to get something big. If I take anything that's on the left side here, the helium, the oxygen, the carbon, and I fuse them together with other helium, oxygen, carbons, they're going to release energy, right? It's kind of a strange little thing. But if I take larger things that's on the right side of this iron on that side, and I fuse them together, say I take tin and fuse it with tin, they're going to absorb energy. They're going to require energy for that to happen. So fusion can't happen with the larger elements because then it's going to start taking energy away from the environment. But fusion can happen with the smaller ones. That's what's happening in our sun. It's called these proton-proton helium fusion reactions. They fuse together, they release energy, and that's how our sun is being powered by this fusion. So taking all these little smaller particles and fusing together, it's going to release energy. But as you start running out of fuel, this is beyond this lesson right now, but as we start running out of fuel in the sun's going to start running out of helium. It's going to start running out of hydrogen. It's going to create some oxygen, and those oxygens are going to fuse together, and they're going to make bigger elements. And then those bigger elements you're going to run out of oxygen. So what's left over are these bigger elements, and they're going to fuse together to make even bigger elements, right? And they just keep on doing this. And eventually what's going to happen is we're going to have iron fusing with more iron to make this bigger element. And what happens? It starts taking in the energy that it was producing before. And all the way up to that point, the sun is releasing energy. And then when we start running out of those smaller pieces, like oxygen, helium, hydrogen, if I start running out of those, I have to start fusing together bigger pieces. And the more that happens, I get more bigger and bigger pieces, and I start running out of the lower stuff. Eventually, the bigger ones are going to start fused together, and they're going to start absorbing energy from the sun. They're going to start taking energy in rather than releasing it. And the sun will slowly cool down and collapse and possibly explode or create a black hole, depending on how big the mass is, right? So, and this has happened before, right? The majority of the stuff on our planet, like the big stuff, iron, tin, uranium, even helium, oxygen, all those stuff, they were created from the previous sun that has exploded out all these bigger things that fused together. And then it all grouped together because of gravity and created our planets and stuff. So And it's just happened before. Like our sun is a fourth generation star. So it's expected our star is going to just do the same thing. It's just going to collapse, explode, and start all over again in our solar system. Anyway, that's beyond this. We just wanted to know per nucleon, this idea that the larger this number, the more stable it is. That's how much energy is being used to hold it together. That's how much energy it technically has, right? Or how much you need to pull it out. So that larger that number, the more stable it's going to be. All right. But I'll talk about that fusion fission stuff Friday or Thursday this week. All right, so we have these binding energies, and sometimes the binding energy, like I said, it's just not enough, right? This strong nuclear force, because it can only work in these femtometer ranges, and there's this very strong electrostatic force pushing these things out, or electromagnetic forces pushing these things back out. Eventually, as the atom gets larger and larger, more and more protons, the protons are going to be pushing on each other more, so that nature just puts in these neutrons to kind of space them out nicer. But eventually those protons are going to be too far apart from each other to be held together by the strong nuclear force. And they become unstable. Right? So in this next chart here, I know yours is not color, I'm sorry. But this next chart kind of tells us all about these stable atoms. So you can see through here, all of these black dots on my sheet, these are stable atoms. You can see on the chart here, black means stable, red, 10 to the 14 years, that's longer than the age of the universe, right? And then as you go down, the greens they're only stable for about a year, and then as you go down into the white and to the blue, then we have less and less stable elements. They decay because the protons get too far apart from each other, because there's just too many pieces, or there's just too many protons pushing on each other. The strong nuclear force is not enough to keep it together anymore. So you can see it starts off pretty relatively, the N and Z line here, so neutrons and protons. It starts pretty nice, 1-to-1 relationship. So 1-to-1, 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 1-to-1. So right about here, we have 20. Remember, I think 20 is carbon. Let me see what it is. Look at my periodic table here. Yeah, or carbon, not carbon. It's calcium, sorry. So about calcium, it starts deviating from that 1-to-1 relationship. We have too many protons now. So to get more strong nuclear force, we start putting neutrons in there, get that bigger mass defect. But because we start putting in more spacing between the protons, now they can be pulled apart from each other, because that strong nuclear force also kind of decreases as well. So we start deviating a little bit from that. So we need more neutrons to get that stronger nuclear force there. So we get the stronger nuclear force because we get that bigger defect there. But you can see we got lots of unstable stuff here, right? And then it starts deviating more, like, okay, now we have a problem, right? So we need more and more neutrons to try to keep it stable. We need more and more neutrons to keep it stable. Then we need more and more neutrons. And it just keeps following this pattern, like, okay, it starts off really nice down here. Then we need more neutrons to keep it stable. Then we need more and more neutrons. We start deviating away from this line here. But eventually, like I was saying, you're going to have too many neutrons, right? And you have too many neutrons, even with the larger mass defect, the larger binding energy, the strong nuclear force is not going to be enough, because those protons are getting too far apart from each other. And then everything pretty much after this point is just radioactive. And this, if you just look at the chart, I think down the bottom, these are my my proton counts. So like anything after 82. Lead. Pretty much everything after lead is, I think it's about 82. Yeah, pretty much everything after lead is radioactive. Just the way it is. Some are more stable than others. You can see like in this range here, you got some dark red stuff in here. I don't know where that would be, like in the 90s-ish. But they're all radioactive. Pretty much after that point. There's just no way for the strong nuclear force to keep the protons together anymore. There's too many protons. They're too spaced out, and it's going to start decaying. Now what happens is that these elements want to become stable. They want to get back to that black line. They want to be a stable element. They want to, if I'm up here, these guys all want to kind of move down here towards this black line, which would be towards lead, being one of our more stable ones. Or if I'm in this range here, I'm going to try to move one way or the other to get back to that black line, right? So I'm going to try to get to this black line to become more stable. How does an element do that? Well, it has two, or essentially three different ways to do it. Now, the reason I started off with two is because the two ways we talk about it are alpha and beta, or beta, right? So alpha and beta, but the thing about beta, it comes in two different, different word for it, two different flavors of it. You got beta negative, and then you also have beta positive, right? So there's two different betas. There's only one alpha though, right? So we got alpha decay and we got beta decay. And those two things can actually change the makeup of the element enough to try to move it towards a more stable configuration. So let's talk about those, right? So alpha, beta, and gamma. What gamma is, you remember the video she was talking about, it doesn't actually physically change the structure of the atom. It kind of just changes the configuration of the atom itself. Like, it still has the same number of protons and neutrons. It just changes the configuration a little bit. And then in that process, it just releases energy. It's not going to change any of the protons and neutrons. Yeah. But what happens in alpha decay and beta decay, my proton and neutron counts start. They change. Now, alpha decay is pretty easy, right? It's a pretty simple process. So what it does, it's just a release of a alpha particle, but an alpha particle is just a helium nucleus. So what this is a helium nucleus. And helium nucleus, just a helium-4 nucleus, is going to be this. Now, what's very important is in helium nucleus. It doesn't have the electrons. It's not a helium atom. There's the difference between atom and nucleuses. So a nucleus is just the nucleus without the electrons, right? So what that means, it's not balanced out. It's not neutral anymore. This is just two protons and two neutrons, right? So that means it is a positive ion, right? So it's a beam of positive helium nucleuses, right? And where they come from, they're just in the atom already. These are just two protons and two neutrons that are just popped out of the nucleus, and what's left behind is just what's left behind, right? These did exist before. I stopped the video before and I said, these neutrons and these electrons and these neutrinos, that they didn't exist. That's beta decay. The helium one, the helium nucleus, is alpha decay. Those guys were there, and they just got popped out. That's it. There was just too many neutrons and too many protons. They just pushed themselves out, and off they go. Okay? And what's left behind is what's left behind. Okay? So beta decay comes in two different flavors. Right? Now, how beta works, it changes a nucleon from one flavor to another flavor. So one, like a proton to a neutron, or a neutron to a proton. Right? Now, we just represent this, and essentially it's just an electron, or, we'll talk about this later, a positron. Right? I can't erase it. There we go. A positron. Now, a positron is an electron, but it's an anti-electron. It's antimatter electron, which has mostly the same properties, it has the same mass. Okay, the spin might be different, but we haven't talked about spin. We won't talk about spin. But its charge has changed. It's just flipped. So if it's a negative charge, now it's a positive charge. And that works for all antimatter. So if I have a anti-alpha particle, I just have a negative alpha particle. It's just a weird thing about antimatter. It has the opposite charge, right? But it has the same mass and the same magnitude of charge, right? So beam electrons or positrons. All right. So a positron are these anti-electrons, right? We'll talk about both in the next couple of minutes here, actually. Okay, so gamma, what gamma is, so we use different symbols for some of these as well, right? So for helium, for this alpha stuff, we sometimes use the alpha symbol. Sometimes we actually put the numbers on it, so you might see it as 4 alpha, right? You don't necessarily have to, because alpha is alpha. You know what it is. Well, most scientists will know what it is. You notice that when we also put it there, we don't actually put the charges in. It does have a charge, right? Alpha particles are 2 positive. But scientists, for some reason, kind of ignore these charges. And those charges are very important when we're trying to figure out if things balance out nicely, because there is a conservation of charge. What I start off with, I got to end up with. Just the thing. Beta particles, right? So we either write them as a beta positive, which might be, remember down here, or a beta negative, so we might put a little negative down there, maybe a little -1, or if we want to write it as a positive one, sorry. So we have beta negative or beta positive, right? You notice we didn't put any numbers on the top part because these are not nucleons. They have a charge, so the bottom is usually denoted for charge. Sometimes we say protons, but the protons are the charge of the nucleus. The electrons have a charge, positive or negative, but they're not nucleons, they're too small. So sometimes you might put a 0 on the top, right? So might put a 0 in these two spots. You don't have to, right? But that's also going to be very important too. All the nucleons have to be balanced out, yeah? But electrons are not considered nucleons. Now, gamma particles. So gamma is just a beam of high energy photons. They're from those excited elements. We just use, let me just change this. We just use the gamma symbol. That's this kind of weird looking Y shape here, right? It's just energy, doesn't have a charge, right? It's just a photon, travels at the speed of light, and that's it. What else? Oh yeah, and we know that they have these charges because of passing through a magnetic field. But this is just using our hand rule here. So we got all these little dots here. That's my magnetic field. We just use our hand rule, or left hand, right hand, trying to determine what charges these are. I don't know how we're going to do this out of the page. Out of the page? Left hand? Which hand am I using? Right hand, left hand? But we can determine if they're positive or negative or neutral. You can see the gamma there going straight on through doing absolutely nothing. Okay? Now, if there was a gamma positive or beta positive, and there is, you would notice the beta positive go the other way too. So there could be a beta positive, but this one would be the beta negative, right? And beta positive do exist. Antimatter exists. It has been explored, and movies are based on it. And it's every time there's a lightning storm, there's antimatter being produced. So this stuff actually exists. Okay. So in alpha decay, and you can see I already messed this up. There's supposed to be something here. But alpha decay is just the emission of 2 protons and 2 neutrons. They're just kind of stuck together, and off they go. And when they do that, they just leave behind a new element. Because if I lose 2 protons, if I lose these 2 protons, and I had 90 to start, I'm going to have 88. And I got a brand new element. So I probably should complete this line and make it a little bit nicer. So I started with thorium-227. Thorium-227. I'm going to lose, I'm just going to write the alpha particle first this time. I'm going to lose an alpha particle. So I'm going to lose 2 protons. And there's it's on our formula sheet. I know it's going to end up being backwards on yours, but on the formula sheet down here, there's a bunch of these conservation laws, and one of them is conservation of nucleons. It's number 8 on this chart down the bottom here. Conservation of nucleons. The one above it also says conservation of charge, number 7. So what's important is that nucleons have to be conserved. If I start off with 227 nucleons and I lose 4, I just have to have enough to make sure I end up with 227 afterwards. So 227 minus 4. Why am I doing that on my calculator? I don't know. We have 223. So that's where the 223 comes from. These 2 top numbers have to add up to the original amount. They got to be conserved. And the 2 bottom numbers, they're like my charge numbers. They're protons too, but they're like my charge. They have to be conserved. If I start off with 90 pluses, and technically I have 90 negatives too because I have those 90 electrons, but look at that later on. If I start off with 90 positives and I lose 2 positives, I got to have 88 positives afterwards too. But now because we're at 88, we're at a brand new element. We're no longer thorium. So we go to our chart, our PR table, and we find 88. Oh, it's radium. So we are radium now. Now, here's the problem. So there's a conservation of charge, right? So this is usually kind of ignored when I say write the alpha decay, this is what you write, right? But there's a better way to write this. I'm just going to move this down just a little bit. Okay. Now, what we know about this, okay, my thing is, oh, I'm in the wrong thing. What we know about this is that when we lose these pieces, the structure of the atom hasn't quite completely changed. All these electrons are still in those electron shells of thorium, right? So there's this weird transition period right here where radium is excited because it's still in the thorium energy shell orientation. So it's pushed out these protons and neutrons, but it still kind of thinks it's thorium. It still has actually the same number of electrons as thorium too. If you really think about the charges, we'll get to the charges in a bit. This is a negative ion because it still has the 90 electrons, but only 88 protons. So it's a negative charge, a negative thing, but that's the different story. But it has the thorium energy shell, so it's excited. The electrons are in the wrong spot. So there's this kind of transition here, and after the transition, it becomes unexcited. So this radium now, this radium is now unexcited, and in the process releases gamma energy, right? So in the first one, it releases kinetic energy because the masses don't match up. We'll talk about that in a bit. And then the second stage releases this gamma energy because all these electrons are now moving around between states. Remember, when electrons move, they have to release the energy somehow. They release it as photons, in this case, gamma. Okay, so that's important. But what's also missing, which usually a lot of people just don't write down, but they are there, is that these are technically ions, right? Like this is positive and this one's a negative one. Because it starts off neutral. We talk about a thorium atom. When an atom is neutral, so everything here is neutral, which means if we have 90 protons, we have 90 electrons. So we have 90 electrons. When I lose these nucleons, this 4 and 2, these 4 nucleons, it's not taking electrons with it. So it's still leaving behind 90 electrons. But we only have 88 protons. So we have more electrons, more negative. So we have a negative charge on that radon. Or radium, sorry. Not radon. Right? Yeah, that's right. Okay. Now, what we notice is that there's a lot of conservation of matter, not mass, which means what you notice that all the nucleons all match up. We start at 227, we end up 227. There's a lot of conservation of charge, so all the numbers on the bottom match up, but it's not the law of conservation of mass, right? Because we have actually, if you think about this, we've lost mass. Right? We'll do a calculation on this later on. Right? We've technically lost mass. And where does that mass go? Well, it just goes in the energy. It's just like the other way around, right? If we before, well, it's not exactly the same as the last one. If we lose mass, we gain energy because it's got to go somewhere, right? So it's not a law of conservation of mass, it's a law of conservation of matter, technically. Or in this case, nucleons, if you want to actually write that down as nucleons, which I'm going to do right now. Right? So let's just change that. So this, it can be written as nucleons instead. Right? So law of conservation, nucleons, the numbers on the top. So this is the top. Okay? And this is the bottom. The charge is the bottom. Okay, so those helium nucleuses, these alpha particles, you just write them as He, but if you're going to write them as He, you probably want to write it as the 2+ version of it, probably better. So here we're going to write out what is the alpha decay of uranium-234. Okay, so uranium is past that like 92 mark. It's unstable. It's going to decay. It's going to want to try to get towards that black stable line there. So to do that, it's going to try to eject some helium maybe. So maybe it's just too many neutrons, too many protons. Let's get rid of some of them. So it's going to eject this helium here. And I want to know what this other element is called. Now this other element is called the daughter particle. Right? There's no such thing as the son particle, so it's the daughter particle. So we have the parent. So this side over here, this is the parent. Right? And I want to know what the daughter is. Now the radiation is never the daughter particle. The radiation is just radiation, right? So this helium here, that's just radiation. It's the alpha particle. We don't call it the daughter. It's the other bigger piece that's not the radiation. We call it the daughter. So let's figure out what that is. Okay. So we start off at 234, 92. We are going to lose 2 charges, 2 protons here. So that means I'm going to end up with a 90 on the bottom because 90 plus 2 is 92. It has to be conserved. So based on that, I should be able to just tell you, you should tell me what it is. So like my periodic table, that's 90. So we've seen that before. Oh, 90. We know it's 90. That's thorium, right? That's thorium. Okay, now what type of thorium? What is the isotope of thorium? I can't just say thorium. There's lots of different thoriums out there. Which isotope do I actually have? So if I lose 4 nucleons and I start off with 234, I'm going to end up with 230. So we have thorium 230. Okay? Now, remember what happens here. This thorium still thinks it's uranium. It has all the electrons of uranium. They're in those uranium shells, very specific to them. So this guy's excited. So I'm going to put a little star there that is excited. So he's going to actually become unexcited eventually. Those electrons are going to shift to the right spots. And when they do that, they're going to release this gamma. Okay? So a lot of the times we just don't write the middle part. We usually just write this last part and this first part. Maybe this arrow too. Well, this middle part's like an intermediate step. But it is there, right? It will be excited, and then when it becomes unexcited, it's going to release some energy. Okay, the bottom part there is just talk about what I said about daughter and parent. Okay, let's try another. Well, first of all, okay, let's do these ones. So here, these first 2, at least alpha particles, the releasing the alpha particles. Are they possible based on what we have here? So I'm just checking to see, is the nucleon count true? And is the charge count true? So I'm going to let's look at the charge in these first 2. So 2 and 82, that's 84. So that works. Okay, so the charge works on that one. Let's look at the top though. So this is 214. 214, okay, so 208 and that, oh, I think that's only 212, right? Yes, this is only 212. And this is 214. So it doesn't work. So this is not possible. Based on what we have here. Maybe it's going to have to release some other particle to account for the extra 2 pieces. I don't know what that would be. Maybe it's a neutron or something. Let's check out this next one based on what they wrote here. So the bottom, does it add up? So start off at 90, 88 plus 2 is 90. Okay, that works out. So a little check mark there. All right. Then my next one here, so we start off with 230, 226 plus 4, that's 230. Okay, that works out. So this is good. This is a viable solution there. Not bad. Okay, little happy face here. All right. And then let's check out this last one. This one's here a bit different. We have a neutron. Okay, so you know what? You look at the things about the neutron there. The neutron has no charge, all right? So neutrons have no charge, so that's why there's a 0 on the bottom here. But a neutron is a nucleon. It is part of a nucleus, so that is a nucleon, right? So that's why there's a 1 on the top, okay? Let's just see if it works mathematically. So we got 60 here, 60 plus, oh, that doesn't work. That's 61 on this side, but yeah, so this is not going to work. How about I put a sad face somewhere? Let's put a sad face. That doesn't work. So this is like 61 over here. The bottom also doesn't work as well. There's 28 and then there's 27 to start off with. Okay, let's try out another one here. So it's to predict the daughter particle. So I'm going to want to know what isotope is being produced through the alpha decay of radium-226. And I'm going to skip the intermediate step here. So I'm going to start off with radium-226. So radium, radium is 88. Is it? Yep, it's 88. And then it's going to undergo alpha decay. So it's going to shoot off. Now the order of these 2 particles doesn't really matter as long as they're on the product side here. It's going to shoot off this alpha particle, right? And I just want to make sure everything kind of balances out. Like I said, a lot of scientists will just kind of ignore the charges. They are kind of useful in some kind of calculations that we're going to do later. But right now, let's kind of No, worry about that later. So we lose 2 on the bottom, so we become 86. 86 plus 2 is 88. So that's where the 86 comes from. The top, I'm losing 4 of those from 2 to 1. So that's going to be 222. Okay. So then we got to find out what this is. Ooh, this is radon because the 86. All right. So Rn. So the daughter particle, so this is my daughter here. I guess spelled daughter, right? Is radon 222. There we go. So I can't just say radon, right? I got to be very specific. It's got to be radon 222. In this very specific case, because we started off with radium 226, in alpha decay it becomes radon 222. Yeah, looking good. Oh, and that little gamma, right? Because remember, I skipped the intermediate step. It was excited somewhere in the middle, right? And after it becomes excited, it's going to release that gamma, right? Yeah, release that gamma. Okay, so alpha decay has relatively poor penetrating power. What that means is because it's so large compared to all the other ones, and it's moving relatively slower than all the others, it could be stopped by just simple paper or cloth suit, right? So when you think about like people in radiation settings and they put on those little outfits, those outfits could technically be made out of just thick paper, right? Maybe they're made out of kind of a plastic material as well. But really what they're trying to do is they're trying to stop these alpha particles from getting into the suit, but they don't have to be very thick and cumbersome. They just have to be thick enough to stop the alpha particles. Now, the problem with beta particles, because they're smaller and faster, they're going to be able to get through that suit like nothing, right? To stop them, you're going to need like a metal aluminium suit, but that's cumbersome. So a lot of scientists, they don't deal with that, right? They just want to try to stop these bigger guys from getting in because it's easier, right? Rather than just walking around in a big metal suit and stuff. So, also we have a problem too, right? If alpha radiation gets into your body, right? It's a little bit different than beta, but alpha, because it's so slow and so big, it has a hard time trying to get out, right? So if you inhale this, so there's also a very good reason why you want to stop it. This is my picture of my lungs here. I don't know what lungs actually look like here. Does it look like lungs? Okay. If I inhale my alpha radiation, so like maybe through dust or something, and it has some alpha particles in there, actually probably radon or radium particles. Let's just say it was radon or radium particles. So I inhale some of those 226 guys from up there. And I inhale those. As they decay inside my lungs, they're going to start shooting out, right? But they can't get very far because they're slow, they're big, so they're going to start interacting with the cells around the lung tissue or the lung tissue itself, right? So they're not going to get very, very far. So they're going to cause some damage, right? Now, if it was beta decay, if you inhale something that's going to release beta particles, those beta particles, because they're smaller and faster, they can pass through material more easily. There's a higher chance that they're going to get through your body without interacting with it, right? So it's safer to inhale beta particles or things that are going to react or decay through beta decay than something that's going to decay through alpha decay. Safer. There's still a chance that beta decay is going to hit your whatever is passing through and cause some problems, but it's going to get out of your body faster. It's going to cause less problems, right? But alpha decay is going to cause lots and lots of problems, right? If it gets inside your body. So it's good to stop it. So that's why you wear your suit, right? Yeah. Okay, beta decay. Lots of time here. Okay, so beta decay, similar process. An atom or an element, so it's like a nucleus that's unstable, is going to try to become more stable, and one way to do it is through beta decay. Now, beta decay, this is an electron here, comes in, like I said, two flavors, right? positive or a negative, right? So we can also write this as a positive, which is essentially just a positive electron, which could also be written as this as well, right? So you don't have to write the little negative one. Positive one's there. You can write it up on the other corner there, but it means the same thing. Okay. So these ones here are called positrons, right? Positrons. And this is just electrons. Now these electrons are exactly the same as any other electrons, right? They're just from the process of beta decay. The positrons are different. They're anti-electrons, but they're from the process of beta positive decay. What also happens, because of this weird discussion about conservation of momentum, if something undergoes decay through beta decay, and if we just deal with these two particles, say it's just carbon here changing through, this is proper, yeah, carbon changing to nitrogen. If this is all there was, then those electrons and those nitrogen particles will always be traveling the same speed. But it doesn't. That doesn't happen. Some electrons and some nitrogen atoms are traveling faster and slower than others through these decays. So there must have been something else that could be taken away a little bit of this energy and momentum to cause the varying speeds of these beta particles. And they've since have detected it. So this representation that I've drawn here of this carbon beta decay of carbon-14 is wrong. Okay, so we got to add in this little extra piece. This is just not enough to account for all the conservation momentum. There had to be something else. So it has a neutrino, right? Now, this very particular one is an antineutrino. So it's very key. So it's a beta negative, which is the regular electron, right? And it has an antineutrino to go with it. So an antineutrino is just represented by this little V shape here, maybe a little rounder V shape. But we're going to put a little line on top of it. That little line represents antimatter, right? So this antimatter particle is being produced through beta negative. Now, beta negative is just a regular electron, not just regular matter, right? So this is a regular matter particle, and this is an antimatter particle that's being produced, the neutrino. So this here is my antineutrino. Now, what a neutrino is, not really super important, but it's this highly unreactive neutral piece of matter. And it's weird. Like, it's highly unreactive. Like, as the sun is producing all these, the sun is doing all these nuclear reactions. It's producing trillions and trillions of these neutrinos, which are passing through the Earth undetected all the time, right? It's very hard to detect one of these. They need a special detector deep within the ground with this really heavy water, fluorinated water and stuff. And even then, I think they got these little flashes of light every time there was a reaction. Maybe they got like 1 or 2 a day, right? So they're highly unreactive. And there's zero charge. And you notice that here, there's nothing here. There's no charge, and they're too small to be considered a nucleon. So there's 0 with 0. So if you were to write something here, maybe I'll just put it in a different color, you would write a 0, 0. There's no charge, and this too small to be considered a nucleon. So you don't count it as part of one of the numbers on the top. You don't count it as part of the numbers on the bottom. Okay? So what you notice, there is a conservation nucleon. So you notice that on the top, 14, 14, 0, 0, they all add up. You got to start off 14, I end up with 14. On the bottom, we got conservation of charge, right? We got 6, and on the other side, we had to end up with 6 as well. So 7 minus 1, because it's beta negative, plus the 0, I guess, right? That adds up to 6. We had 6 to start off with. We end up with 6. Conservation, right? Conservation of charge. So technically, this nitrogen, if you really think about it too, if I start off with neutral, we have 6 electrons. And now over here, we still have 6 electrons, right? So we have 6 electrons, but we have 7 protons. So this is now a positive particle, right? It's a positive ion. This electron is obviously a negative electron, right? So it's negative. So those will add up to 0 eventually. The neutrino is neutral. There's no charge, right? So there's still 6 electrons here. Okay, let's look at this. So what's happening here, if you were to break it down, so we're going to break this down. So I'm just going to break it down a little bit more. So over here, carbon-14 has, if I were to write this out, we got 6 protons. 1, 2, 3, 4, 5, 6 protons. Let's just make those black there. And because of the 14, we have 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8. So we have protons and we have neutrons, right? And over here, we have 7 protons now. 1, 2, 3, 4, 5, 6, 7. Remember, Z is for protons. And we have 7 neutrons. 1, 2, 3, 4, 5, 6, 7. So you can see it's changed, right? We had 6 protons, now we have 7. We had 8 neutrons, now we have 7. So we gained a proton, but we lost a neutron. Okay. Over here, we have just an electron shooting off here. We have this little neutrino just kind of shooting off like crazy. So if I were to break this down even further now, I start crossing off what they have in common on both sides. So if I start crossing off protons they have in common, there's 6 protons here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, we have an extra proton here. And then over here, we have 7 neutrons on the product side. 1, 2, 3, 4, 5, 6, 7. I'm going to cross off 7 on this side too. And we're left with 1 neutron on the reactant side. So this neutron here, that's this big guy right here, and this proton, that's really what changed, right? It went from a neutron to a proton. And out comes these 2 particles. All right, this electron, technically it's a negative electron, not a positron. Proton is positive, obviously. All right, the neutrino is not charged. But they just come out of nowhere. So this electron is not an electron that existed before. All right? So that electron doesn't exist. This neutrino didn't exist. This proton technically didn't exist before. So what happens is the neutron just phases out of existence, and then an indeterminate amount of time later, a proton comes into existence. And there it is. It's a proton. It's just kind of weird. We'll talk about later that there's this kind of intermediate particle, this kind of what we call a virtual particle. It's a boson. These bosons, they just exist for a small amount of time to allow this transfer to happen. And we'll talk about that later. It's like the very last thing we talk about in this chapter. All right. So what element will the decay of thorium produce? So let's imagine we're talking about beta negative decay. So let's specify this. So this is beta negative. I'm going to say beta from now on. Okay, so let's just imagine that. So we have thorium. So thorium we've done so many times. We've got thorium, that's 90. It doesn't specify what kind of thorium. Do we have a thorium up here that we're using for an example? No, not really. Let's just say 230. All right, I know I probably should be a bit more specific on this one. So 230. All right, so 230. All right, so it's going to undergo negative beta, so very specifically saying beta negative there. All right, so beta negative. What does it produce? All right, so the bottom numbers have got to add up. So if this is -1, this is going to have to be 91, right, to make sure it also adds up. The top, because betas are so small, they're not considered nucleons. So we could say there's a 0 here if you want to. You don't have to write it. But all the numbers on the top have to add up, so there's got to be 230. All right? What is that? Let's probably write something in there, that spot, before I go too far. What's a 91? Protactinium. So that is Pa. All right. Now, again, I've kind of skipped a step before. This protactinium has the same electrons as the thorium used to have. The thorium had 90 electrons. This protactinium has 90 electrons as well in the thorium state. So technically, this guy is also excited. Yeah. Also, beta negative will produce an antineutrino. So that's going to be very important. There's got to be this antineutrino to go with this beta negative here. So those guys always go together. Right? So after this guy becomes unexcited, I'm just going to rewrite this. Okay, this is. I kind of reordered them for some reason. Okay, he's going to become unexcited. He's going to release more gamma. So it releases more gamma. So every time something becomes unexcited, it's just going to release that gamma particle. Okay. So you're going to realize very quickly, in all these decays, there's always going to be gamma decay to go with it. Right? I didn't write that up here. I probably should write. There's gamma over here somewhere. Right? What about the beta decay? So again, beta negative. So this is just regular of actinium-227. Did I actually spell that correctly? Sometimes I mess this one up. Oh, it's actinium-227. Okay. So it should be actinium. This might be like an old spelling of it, or maybe I just misspelled it. Well, let's imagine that this is actually spelt actinium-227. Okay, so actinium-227 is 89. That's an AC-227. Okay, it's undergoing beta negative again. So very important. We have beta negative and we have the antineutrino to go with it. So they have to go together. I'm going to skip the intermediate step. This kind of idea that's excited at this point. I'm just going to skip that. I'm going to go right to the end. And in the end, it's going to release that gamma as well. So everything on the bottom's got to add up. So we got 90. Right? 90 minus 1 is 89. On the top, everything's got to add up. So we've got 227 still. Okay? So now we have thorium, 227. And a little bit of gamma. Cool. Now, how much energy would you expect to be released from this? All right, this is a big question. Am I going to have enough time for this? Is it an hour or something? Yeah, I might have to talk about that. Oh, we should be able to talk about that. All right, so let's talk about this. So we are going to figure out how much energy is actually released through this reaction. I don't know why I skipped so far ahead. Through this reaction of thorium-234, or 234. Now, we didn't do this for helium, but we could do this exact same step with the alpha decay. Okay, we can do exactly what we're doing here. So let's just talk about this one. This one's going to be pretty fun. So what I want you to do is pull this sheet out, okay? So this should be handed. Oh, this is a weird one. It's kind of blurry. But pull this sheet out. This should say on the top here, it should say atomic masses of selected isotopes. It's a big chart of numbers, different isotopes here. On it, it should say thorium-234. You should probably look for it. Yeah, thorium-234 down the bottom of the second column there. All right? So what this is, these are all my atomic mass units of different isotopes. And we're going to use this to help us figure out what is the mass defect in this reaction. Well, first of all, we've got to figure out what the reaction is. So let's just imagine, again, this is beta negative. Right? Beta positive gets a little bit more confusing. All right? That's next page there too anyway. So let's do beta negative again. So we got thorium-234. So I'm going to write that down. 234 thorium. Thorium is 90 on the bottom there. We've done that a lot, so we kind of know that. And it's going to change into, or undergo beta decay. So here's my neutrino, and is it going to be 91 again? Yeah, it's going to be 91 again. So this is protactinium. So we did this one before. The bottom numbers got to add up to the 90. So looking good. Protactinium is PA. Yep, PA. Not too concerned about the charges at this point. And there'll be some gamma. Right? The gamma energy we can't really calculate. That's too complex for this course. But we can calculate the other energy that's being released, this kinetic energy, because these guys are flying off really fast in all different directions. But we calculate that by using the mass defect. So what we're going to do here is we're going to look at this. Now, these numbers that are on this chart, these are all atom numbers. What that means is that these numbers are for atoms that are neutral, not nucleon numbers. These are not nucleus numbers. These are atom numbers, and atoms are neutral things. So thorium, I'm assuming it starts off neutral. Probably a good assumption here. But this protactinium is not neutral at this point, right? So I'm just going to put in a different color here some charges that we're going to have to worry about, right? So this beta is negative, but this protactinium is positive. It has 90 electrons still. This other electron that's over there, this electron, this beta negative particle, that electron didn't exist before, right? So that's a brand new electron. So we have 91 electrons essentially, but the protactinium only has 90 because it started off with 90, right? So it's 90 electrons, it has 91 protons, so it's a positive 1 charge. It's missing an electron. So this is, I'm going to write that down. It's missing 1 electron, right? It has 90 electrons. Okay, this has 90 electrons. So these electrons are all accounted for. This extra electron, this plus 1 electron over here that we have, this is 1 electron here. It wasn't there before. So keep that in mind. So thorium-234, if you look at my chart here, has a mass before the reaction, an atomic mass of, so I'm just going to put here mass numbers. In atomic mass units, 234.043601 atomic mass units. Okay, so that's what, just reading off the chart, thorium. So this here, if you need some of these numbers, I'd have to give them to you. Right, you're not going to remember this. You're not going to be given this chart. You'll just be given it in the question somewhere. Okay, so we have that number. That's what we start off with initially. What we end up with is these 3 pieces. The photon has no mass, it's the massless particle. But we have these 3 pieces. So an electron, at the very bottom of this chart, there's an atomic mass number for an electron. So in a single electron, that's what this is. This beta negative is an electron. So it's 5.8. No, that's not right. 5.8. It's 5.48799 times 10 to the negative 4 atomic mass units. It's really small. Electrons are small. That's why we don't consider them nucleons. They're too small for that. A neutrino, even smaller than that. I don't have the actual number for it, but we won't even include it. It's just too small, right? Too small. It has mass, it's just too small for this calculation. It won't change any of the numbers, right? The protactinium, now what's going to be important about this protactinium is I'm going to write down 2 things here. I'm going to write down the atomic mass that's on the sheet here, protactinium-234. Now the thing about that number, this is for the atom. Right? So this number is for the atom, but this protactinium is not an atom, it's an ion. It's missing an electron. So what I need to do is I need to minus, because I'm missing this electron. Let's put a little asterisk here. I need to minus away an electron out of this number. Because this number assumes we have 91 electrons, but we only have 90 electrons. So we have to minus out this number. Times 10 to the negative 4 atomic mass units. Now, if you look at this very carefully, I had to minus out an electron, but we also got a brand new electron over here. So these 2 things, this one here, we had to minus out this electron, but then we also added in this other electron that's just brand new to the whole system. They just cancel each other out, don't they? One's a minus, one's a positive. Mathematically, they just cancel each other out, which is kind of nice. So what happens on this side is just ends up being the protactinium number. Okay, so now we have our 2 masses. If you want to go through and do all the adding of all those numbers on both sides, you could see that they end up being the same. Or the left the right side, the product side, those two electrons just cancel each other out. But if you look at these two masses now, I start off with a slightly larger number. You see right here, this starts off 601 or ends off with 601, but now this one ends up with 308. Where did the mass go? Well, you're right. It changed into, I'm assuming that you answered that question. It changed into energy, right? So we can find the mass defect. So I could take my final minus my initial. Well, I'm running out of time here. We could determine the difference, and you can see that this is going to be a negative number, and hopefully I can finish this in just the amount of time here that I need. Actually, I have no idea how long class is supposed to be. I think I'm getting close to the end. Did I type that incorrectly in my calculator? I'm assuming I did. I'm kind of rushing myself. So we have 0.000. I think that's enough zeros. 1, 2, 3, 1, 2, 3, 4. So 293 atomic mass units, but it's negative. Okay, so we've lost some mass. How much energy is that? So we're going to use our E is equal to mc squared formula to figure that change of energy. But before I can use this formula, this mass has to be changed into kilograms. So we're going to times this number by 1.66 times 10 to the negative 27 kilograms for every atomic mass unit there. And I can figure that number out. So let's times those together. Times that. 0.66 times 10 to the negative 27. I don't know if they give us a better number. No, we're just going to use that number. So it's negative 4.8638 times 10 to the negative 31 kilograms. So a really small amount. This is actually less than an electron amount change here. And then I can use that in my calculation. So times this with c squared. So let's make sure you square that c. And we get this is going to be a positive change. I lost mass, I gain energy. Negative 14 joules. Okay. Now, just so we could practice this, let's just change this to electron volts here. So remember that 1 electron volt is 1.6 times 10 to the negative 19 joules. So we're going to use this ratio here and I guess technically divide. And we get 273,589 electron volts, which, if I'm going to get to scientific notation, the electron volts that we're trying to avoid scientific notation. So if we're going to change it to the proper sig digs, I'm going to change the prefix. So this will be 274 kilo electron volts. But it didn't specify that. Does it specify that? No, it doesn't specify that. Okay. So there we go. How much energy is released? Either joules or electron volts. All right. So I will see you tomorrow. And we'll talk about a little bit more complex question, this beta positive stuff, and how much energy that's released, and decay chains, and then half-lives. Yeah, pretty good. All right, I'll see you tomorrow. Bye.